What is a Curie point and why is it important to a rice cooker? With a rice cooker, you have a set amount of water, a set amount of rice, you flip the switch, you wait, the switch flips back up, and then you have a perfect pot of rice. So the challenge here is, when do we know when the rice is done cooking? When cooking a pot of rice, we know it's done when all the water is gone. So how do we go about detecting this? Do we take the weight from before and compare it to the weight after? Do we use a moisture sensor? Do we take the direct temperature measurement? Actually, it's none of those. It takes advantage of something called the Curie point. The Curie point of a magnet is a point at which a magnet loses certain magnetic properties due to the high temperature. As shown, we've taken the rice cooker magnet and attached it to a heater. As the temperature rises, you can observe the Curie point. You can see the magnet when it falls from the stand, losing its magnetic properties. Towards a certain temperature, our magnet becomes weaker. We have our magnetic properties because of the alignment of dipole moments. Each ordered magnetic moment begins to change, and our dipoles become misaligned. Under the pot, there's a spring-loaded button that has a magnet within it. When the cooker is turned on with the lever pushes the magnet up and then sticks to the bottom of the pot. This is important because now the magnet is in direct contact with the pot, which is in direct contact with the heating element. Therefore, the magnet will be as hot as the pot is. The temperature of the pot is important because of the water within it. At sea level, the boiling point of water is 100 degrees Celsius or 212 degrees Fahrenheit. No matter how much heat or energy you apply to a pot of water, it will not exceed its boiling point temperature as long as there is liquid water present. This is important because the Curie point of our magnet lies above 100 degrees Celsius. The water regulates the temperature of the pot, meaning that the pot cannot exceed 100 degrees Celsius and therefore the magnet cannot either. Once the water is gone and the temperature is no longer being regulated within the pot, our magnet can now reach its Curie point. It will lose its magnetic properties and will no longer stick to the bottom of the pot. The magnet will drop, flipping a switch or the copper contact you see here, switching our circuit from cook mode to warm mode. Shortly after cooking, you can see that when we attempt to flip the switch again, the cooker will not stay in its cook mode. This is because our magnet is still at its Curie point and it is still too hot to stick to the bottom of the pot due to its lack of magnetic properties. For our basic circuit, there are two pathways being taken here. There's a pathway being taken for our warm mode, and there's a pathway being taken for our cook mode. What is happening here is that we have a resistor and a heater. When cooking, we have a heater running at full power, but when we're using our warm mode, we want to step down that power. That is why we have the resistor. The equation for power is V squared over R, meaning that power equals voltage squared over resistance. The resistance of our circuit is 50 ohms, and our power supply is 120 volts, or the standard wall power in the US. Putting these into our equation, we have 120 volts squared over 50 ohms. This gives us 288 watts. Now we take into consideration our other pathway. Now we have a 330 ohm resistor as well as our 50 ohm heater. Since they are in series, it is just 330 plus 50 ohms. Putting this to our equation, we now have 120 volts squared over 380 ohms. This gives us roughly 38 watts, which is significantly lower than the power output of our cooking function. When our switch is closed and it's set to cook, we are bypassing our resistor. Therefore, our heater is being directly powered by our power supply. When our switch is open and there's no longer an alternate path of least resistance, we are going through our resistor. Now that we are going through our resistor, our power is being stepped down, and now our heater is receiving less power. Previously, when showing our magnet being dropped at its Curie point, you may have noticed additional weight in the form of a binder clip. That is because our Curie point of our magnet is actually much higher than 100 degrees Celsius. If we were to wait to reach a true Curie point of our magnet, our rice would start burning. The additional weight is analogous to a spring within the rice cooker. There's a spring within the rice cooker pushing the magnet away from the pot. The magnet is strong enough to oppose this spring force, but as the magnet begins to become weaker as it approaches its Curie point, the magnet falls away much earlier. Therefore, with some tweaking to the spring, we can have the magnet fall away right above 100 degrees Celsius.